Welcome to the debate. Today, we are engaging with a really profound mathematical divergence at the very heart of how we understand the fabric of the universe. We are looking at the fundamental nature of calculus, and specifically, the transcendental constant pi. The central question we are tackling is this: should pi be understood as an analytic truth that we approach asymptotically within a perfectly smooth continuum, or is it a structural reality enforced by a discrete, almost pixelated underlying lattice?
Right, and it's a huge distinction.
It really is. And this rigorous exchange emerges from two completely fascinating foundational texts. We have Gibsonian field calculus and pi in a discrete world. Now, throughout our discussion today, I am going to defend the Gibsonian discrete token calculus. I'll be arguing that pi is structurally enforced within a fundamentally discrete reality.
And I will be advocating for the classical Ramanujan analytic framework. I'll be defending the position that pi is an infinite, transcendental truth. It is best approached through the smooth continuum, where its profound elegance and extreme mathematical compression are most fully realized.
So this set the foundation for my position. I want to argue that the Gibsonian W-Field calculus does something genuinely revolutionary. It treats discreteness as a fundamental physical reality, not just some numerical approximation of a continuum that we resort to when our computers just aren't powerful enough. I mean, for centuries, our mathematics has relied entirely on the infinitesimal limit. We have assumed that to find exact truth, we absolutely must shrink our step size, our delta x, down to absolute zero. But the Gibsonian framework explicitly abandons that assumption. Its core innovation is taking the step schedule, which it calls T of n, and elevating it to a first-class mathematical object.
Which is a bold move, definitely.
Right. Because by doing so, it allows for exact, rigorous mathematical identities, things like the discrete fundamental theorem of calculus, but without ever needing to invoke the concept of a limit. Under this framework, pi isn't just an endless string of decimals waiting to be calculated. Pi is a rotational closure condition. It is a structural necessity for circularity to exist at all in a discrete universe, stabilized by a very specific exact log oscillatory correction. Essentially, it fundamentally redefines what calculus is allowed to mean when reality itself is quantized.
Well, what fascinates me about Ramanujan's approach is how it completely bypasses the need for all that mechanical scaffolding. While I can certainly appreciate the structural ambition of the Wheatfield calculus, the unmatched elegance of Ramanujan's analytic number theory simply cannot be overstated. Ramanujan doesn't fight the continuum. He assumes a perfectly smooth reality, and by doing that, he achieves this extreme compression of transcendental information. His hypergeometric formulas, specifically his famous infinite series for calculating 1 over pi, they achieve what we call exponential convergence. With just a few mathematical steps, he can calculate pi to an astonishing degree of accuracy. He's basically riding the wave of the universe's continuous geometry, exploiting modular transformations within the infinite real field to effortlessly extract the absolute deepest truths of the circle.
But doesn't that elegance rely on an enormous, entirely unprovable assumption? You're assuming the universe has infinite depth.
I'm assuming the universe's underlying geometry is flawless. Look, my argument is that the Gibsonian discrete approach requires immense, cumbersome machinery to do what the continuum does for absolutely free. Think about it. To make a discrete lattice behave like a smooth circle, Gibsonian calculus has to introduce these oscillatory log corrections and modular projections. It constructs this massive, highly engineered artificial structure simply to recover the rotational isotropy, the perfect symmetry, that the continuous universe already offers naturally. Why on earth build a complex simulator of a circle when the Platonic ideal of a circle already exists naturally in the math?
Because the Platonic ideal might just be a macroscopic illusion. I mean, let's look at how these two frameworks handle the very concept of mathematical error, because I think it exposes a massive bias toward the continuum. Ramanujan's approach is fundamentally computational. His formulas are asking, how do we compute pi extremely fast? And the answer is to suppress the error mathematically via exponential decay. The continuum is assumed to be correct, and the task is merely faster digit extraction.
But the Gibsonian framework looks at this entirely differently. It doesn't view the geometric deviation in a discrete lattice as a mistake to be swept under the rug.
Wait, I have to stop you there. Framing it as anything other than a patch completely ignores the physics of what's actually happening on the grid. When you look at the Gibsonian correction term, this mechanism, C of n equals a times the cosine of gamma times the natural log of n plus phi. That adds an oscillation based on the logarithm of your position. It is exactly the kind of ad hoc mechanism you have to invent if you insist on forcing circularity onto a rigid, unforgiving grid.
It's not ad hoc, though. It's a scale-sensitive measure deformation.
But look at what it's actually doing. If you are accumulating discrete tokens on a lattice to build a circle, the boundary of your circle is naturally going to be jagged. You have inherent pixelation. Ramanujan doesn't need a mathematical term that waves back and forth because his geometry is perfectly smooth from the ground up. The Gibsonian formulation adds an oscillation that intentionally overcounts and undercounts lattice points, simply to cancel out the fact that a discrete sphere estimator is fundamentally flawed. You can call it a measured deformation to make it sound elegant, but it functions entirely as a cosmetic patch to rescue a model that is inherently blocky and anisotropic.
See, I think you are analyzing a discrete paradigm through a heavy lens of continuum bias. You're looking at a digital photograph and complaining that the pixels don't bleed into each other like wet paint. Ramanujan suppresses error mathematically, treating it as a lack of precision. The Gibsonian framework stabilizes error physically via phase oscillation. Think of it like a perfectly tuned instrument. The correction term provides log periodic curvature reinforcement. It actively suppresses resonance drift across multiple scales. It doesn't just average out jagged edges, it enforces structural coherence. And by doing this, it completely redefines the ontology of pi. Pi transitions from being an infinite decimal that we chase forever into a resilient resonant closure constant that ensures the discrete system doesn't tear itself apart. It's an active physical operator, not a passive number.
That assumes the discrete foundation makes any sense geometrically in the first place. Let's pivot to geometry and look at the classic cube diagonal objection, because historically, this has been the absolute death knell for discrete models of space-time. Let's use a real-world analogy. Think about walking in Manhattan. The city is a standard Z3 cubic grid. If you want to walk from Times Square to Central Park, a diagonal movement across the grid, you can't just walk in a straight continuous line through the skyscrapers. You have to zigzag along the avenues and streets. The distance along the axis is one thing, but the diagonal distance is fundamentally longer. Mathematically, it's the square root of 2.
Exactly. The Manhattan distance problem.
Right. And this instantly breaks rotational symmetry. It means that diagonal movement is fundamentally different from axial movement, which implies that discrete spacetime is inherently anisotropic. It has a preferred direction. It is blocky. So how can pi, which represents perfect rotational symmetry, exist naturally as a structural reality if the foundational grid breaks continuous symmetry the literal moment you take a step in any diagonal direction?
If the universe were built like Manhattan, you would be absolutely right to criticize it. But the entire cube diagonal objection falsely presumes that a discrete universe must be built on a Cartesian 90-degree cubic grid. That is a human aesthetic preference. We like right angles. The mathematics of a W-Field calculus deliberately avoids committing to a cubic structure. Instead, it utilizes a tetrahedral or simplicial lattice.
Which is a very clever mathematical tiling, I will admit.
It's much more than clever. It fundamentally changes the geometry. In a 3D tetrahedral lattice, every single node connects to exactly 4 equidistant neighbors. The edge vectors separating them aren't 90 degrees. They are equally spaced at roughly 109.47 degrees apart. This is maximally isotropic for a discrete tiling. And crucially, those 4 fundamental direction vectors satisfy what we call the barycentric closure condition. So vector A1 plus A2 plus A3 plus A4 equals 0. What that means in plain English is that all 4 directions perfectly cancel each other out. There's no inherent forward, backward, up, or down.
So you're arguing that by simply shifting the angles, you completely resolve the Manhattan zigzag problem?
Precisely. Because there are no orthogonal axes to begin with, there is no privileged axial direction. Distance in this framework emerges entirely from the propagation of these simplices, not from stepping block by block like a rook on a chessboard. The concept of a diagonal ceases to be a special problematic path. It is just another combination of equal length edges. By shifting to a tetrahedral adjacency structure, the square root of 2 diagonal artifact is totally nullified. The Cartesian bias is removed, and with it, the argument that discreteness inherently means blocky anisotropy.
Nullified or just hidden deeper in the math? I understand the geometric appeal of the tetrahedral setup, but I have to demand rigorous operator-level proof here, because macroscopic analogies only get us so far. When you look at the continuum, we use the Laplacian operator to govern how things actually propagate. Think of dropping a pebble in a perfectly still pond. In Ramanujan's continuous universe, the Laplacian ensures those ripples spread out in absolutely perfect, unbroken circles, equally in all directions, to all orders of magnitude. If your tetrahedral lattice is just locally averaging out the zigzags of the grid, that anisotropy, that blockiness, will eventually show up in the spectral dispersion of the ripples. The water will eventually look like a square.
I'm incredibly glad you brought up the Laplacian, because the spectral deviation, how those ripples behave at a microscopic mathematical level, is exactly where the Gibsonian framework proves its structural superiority. We can formally compare how waves spread in a lattice by looking at the Taylor expansion of the Laplacian. Now, in a cubic Manhattan grid, when you expand the math out to the 4th order, it yields only axial terms, which we denote as Q4. Because there are no cross terms blending the directions, it proves mathematically that the axes permanently dominate. The ripple in a cubic grid varies widely depending on whether you look straight down an axis or along a body diagonal.
Right, which confirms the cubic grid is definitively anisotropic. The ripples become diamonds. But what exactly happens when you run that same expansion on the tetrahedral operator?
The equal angle symmetry fundamentally alters the spectrum. The 4th order term introduces a crucial cross-coupling component known as the mixed invariant, or M4. The formal deviation is beautiful. Delta lambda 4 of k equals 1/6 M4 minus 1/18 Q4. Essentially, this invariant contains the products of the squared momentum components, literally weaving the axes together. What the math explicitly proves is that diagonal movement is natively baked into the fundamental physics of the lattice.
Let me make sure I am characterizing this correctly. You are saying that the presence of this mixed invariant, M4, explicitly proves that diagonal information doesn't need to be patched later because it's built into the propagation physics from step 1?
Exactly. It proves that diagonal information is embedded directly in the operator spectrum. The tetrahedral Laplacian enforces isotropy at the foundational level. The wave doesn't just treat axes and diagonals differently, it occupies an entirely different symmetry class. That is the formal operator-level reason why the pebble in the pond objection fails here. Discreteness does not imply geometric blockiness if your underlying graph weaves the directions together symmetrically.
I'll acknowledge the mathematical ingenuity of the mixed invariant M4. It is an impressive formal result, and it certainly explains why your tetrahedral grid requires less of that log oscillatory rescue to maintain its circularity as it grows. The anisotropic harmonics are suppressed. But we really have to look at the philosophical cost of this. You have constructed a highly engineered, degree-balanced, barycentrically closed network, and you've combined it with a scale-sensitive correction wave just to replicate a fraction of what Ramanujan achieves effortlessly. Is this not an immense overcomplication compared to the natural, emergent, continuous symmetry of a smooth geometry? Ramanujan doesn't need a mixed quartic invariant to draw a perfect circle. The continuum provides perfect isotropy for free.
But what is actually free in physics? The continuum provides isotropy by assuming an actual infinity of points between any 2 locations in space. That is an enormous ontological assumption. It's a massive blank check. Ramanujan's elegance requires an infinite computational substrate. The Gibsonian framework answers a much harder and, frankly, more realistic question. How do you build a perfect circle out of finite countable hardware? And this brings us to axiom 14 of the W-Field calculus, modular projection.
And this is exactly where the Gibsonian framework loses the plot entirely for me.
Hear me out. The calculus allows fields to be projected into finite cyclic operators. For instance, projecting into a field like Z mod 65,537Z. Think of it like modular arithmetic, where numbers wrap around a clock face once they hit a certain prime number.
But by doing that, by forcing pi into a finite cyclic operator through modular reduction, you are fundamentally destroying its transcendental nature. Pi, by its very definition, cannot be expressed as a simple fraction or a finite state. It is infinitely complex. Ramanujan understands this deeply. His expansions live in the infinite real field, which honors the true transcendental nature of the information. If you project pi into a finite hardware field, it is no longer pi. You have truncated the infinite complexity of the universe into a finite counting game. You've pixelated the divine.
I don't frame this as a destruction of pi. I see it as the ultimate strength of the theory. Ramanujan is bound to the infinite real field. He assumes infinite resources to extract infinitely precise digits. But what if the universe itself operates on finite hardware? Let's use a computer analogy. If you try to calculate pi to its absolute final digit on a laptop, the machine eventually crashes because it runs out of RAM. It hits a memory limit. If physical reality is fundamentally discrete at the Planck scale, it has a finite memory limit. The Gibsonian framework allows calculus to operate rigorously without crashing the universe's RAM.
But a circle in finite RAM isn't a true circle.
It is if the system encodes it structurally. It is not about digit extraction. It is about hardware encoding. By projecting into an oscillatory prime-sequenced modulus, pi is instantiated as a stable rotational operator within a finite substrate. It answers the deeper structural question of how a discrete finite lattice can behave circularly at all without requiring an infinite number of vanishingly small steps.
But look at the flexibility you've had to introduce to get there. If your foundational step, schedule your token measure, is allowed to be non-uniform, and you are actively deforming the measure with an oscillatory correction, and then you are modularly projecting it into a finite field, you have created a system that is incredibly malleable. Perhaps too malleable. Ramanujan's formulas are rigid in their absolute truth. His 1 over pi hypergeometric series is an analytic fact. The danger with the W-Field calculus is that, by turning everything into a discrete token-counting mechanism, you risk losing the absolute certainty that continuous mathematics provides. Exponential suppression of error in the continuum guarantees we are approaching the true value of pi. A bounded measure deformation in a discrete grid simply guarantees you will eventually close the loop, but it doesn't guarantee the loop is the perfect Platonic circle that Ramanujan envisioned.
That completely assumes the Platonic continuous circle is the baseline reality of the universe. What if it's the other way around? If reality is actually a token-weighted lattice governed by a discrete step schedule, then Ramanujan's continuous circle is just a macroscopic illusion. It's a low-resolution smoothing over of the true discrete dynamics underneath. The exact discrete theorem, the product rules without limits, these aren't approximations of the continuum. They are exact mathematical truths in their own right. When we look at the prime-modulated discrete expansions in the source text, the phase function doesn't rely on the continuous frequency. It proves that all the rich harmonic behavior we associate with smooth space can be natively generated by a discrete system.
But have you considered that the cost of abandoning the continuum is abandoning the very concept of exact continuous symmetry in how the universe evolves over time? The continuous wave equation naturally propagates disturbances with perfect smoothness. By trying to replicate a smooth wave on a graph Laplacian, even a beautifully engineered tetrahedral one, you are still fundamentally bound by the limitations of local neighbor hops. Information has to jump from node to node. Ramanujan's analytic framework doesn't hop. It flows. That smooth flow is what allows for his extreme compression of transcendental information. Pi is beautiful precisely because it represents the infinite smoothly enclosed within the finite boundary of a circle.
The beauty of pi is absolutely undeniable, but I would argue its beauty is amplified when we stop seeing it as just a passive number sitting on a continuous number line, when we see it as an emergent, resonant closure, constant, an active physical operator stabilizing a complex, discrete network of tokens. It becomes vital. The fact that the discrete lattice will literally not form a stable rotational identity without that exact oscillatory measure deformation reveals something profound. Pi is enforcing structural coherence across the universe's hardware.
We have certainly covered immense conceptual ground today, and I think we've pushed at the absolute boundaries of both frameworks. To summarize my position in light of our discussion, the classical Ramanujan analytic framework remains unparalleled in its power and its natural elegance. By assuming the smooth continuum, it provides perfect geometric isotropy naturally. It doesn't need tetrahedral engineering or mixed quartic spectral invariants to weave axes together. Ramanujan perfectly compresses mathematical truth, suppressing computational error entirely via exponential convergence. Ultimately, I believe his math honors the true infinite and transcendental nature of pi.
And to summarize my stance, the Gibsonian W-Field calculus provides a rigorous, fundamentally limit-free framework. It removes the need for infinite vanishing points and infinite memory. By utilizing a simplicial graph and treating the step schedule as a primary object, it formally suppresses anisotropy at the operator level. It proves mathematically that a discrete spacetime does not have to be blocky like a Manhattan grid. In this framework, pi is a structural, physical reality, a phase-stabilized closure condition that actually allows a finite, discrete world to manifest circularity in the first place.
I think it is important to acknowledge that both of these mathematical philosophies are internally valid, but they are answering totally different ontological questions. Ramanujan's mathematics flawlessly answers the question of computational precision within the assumed reality of the continuum. He shows us what pi looks like if the universe has infinite depth.
And the Gibsonian calculus answers the structural possibility of how circularity can exist at all within a discrete, finite substrate. There are clear points of convergence here regarding how geometry and wave propagation must be handled to achieve symmetry. But the underlying assumptions about the universe's ultimate reality remain in deep tension.
Analyzing both perspectives deeply enriches our understanding of the universe. It really forces us to ask whether reality is fundamentally smooth, allowing us to glide infinitely along the continuum, or intrinsically discrete, requiring us to carefully count our physical steps. And there is still vast complexity remaining in the source material, particularly if you dive into the exploration of non-uniform step limits and discrete Fourier expansions.
Absolutely. The mathematics we've discussed today pushes the boundaries of how we conceptualize space, distance, and symmetry. We will leave the listener to ponder this fundamental question. Is pi a transcendent number we approach asymptotically from afar, or is it a resilient structural reality we actively inhabit? Thank you for joining us on The Debate.